This video is the supplemental material of the paper, InverseVis, revealing the hidden with curved sphere tracing. The visualization of scalar fields on three-dimensional surfaces is a critical aspect of data analysis and interpretation in various scientific and engineering domains. To properly explore the data, for example to identify regions with high scalar fields, the user must interact with the object. Possible interactions are rotation, translation and scaling. On closer inspection, we discover 4 hot spots. The detection of such interesting regions naturally becomes more difficult the more complex the model becomes. The goal of our approach is to display regions of interest without occlusion, which helps the user gain an overall understanding of the data, recognize patterns, compare data and identify anomalies. Important preliminary work was presented by Neugebauer and colleagues. In this approach, the surface is projected onto 5 cube faces and then unfolded. Here we see this approach on a spherical surface where the cube faces are displayed one after the other. This also allows you to see the hidden sides. This method was developed for aneurysm surfaces and works very well, as the projected sides show the entire object. For more complex objects, however, it is difficult to establish a mental correspondence between the image and the object and to represent the entire model. Another idea to show the hidden sides is to use a mirror. However, this raises completely different questions: what kind of mirror to use and where to place it. In addition to using the mirror, we have developed another approach that we would like to present. The challenge of the 2 new approaches is to combine indirect rendering in the form of surface meshes and direct rendering in the form of signed distance fields. For the mirror, we opted for a quadric that can highlight interesting regions by bending it. Placing the quadric mirror behind the object reveals the back. In the case of the quadric, we have 5 parameters that need to be optimized. The question still remains as to how we can find the best parameter combinations. Another completely new approach is InverseVis. This approach is based on the idea that light rays are deflected under the influence of high-mass objects and even collide with the object. InverseVis also reveals the back of the surface here. A simplification of the approach is that we let the light beams start from the hull at a certain speed. But here, too, the question remains as to how to find the optimum parameter, in this case, the initial velocity. In the following, we want to clarify the question of which energy we want to use to optimize the approaches and how we calculate the best parameter combinations. First, the image is divided into 2 regions. Firstly, in the directly visible part, and secondly, the area that is responsible for displaying the hidden areas of the surface. Based on an importance function, the parts are integrated across both screen regions. Interesting importance functions are, for example, the total visibility or the display of high scalar values. To find the optimum, we use a gradient descent with a golden ratio line search. Here we see the optimization of the mirror. At the end, we recognize a hot spot on the leg of the object at the bottom left of the video. The same again with InverseVis. This time we also recognize a hot spot that must be on the back. We also have the option of finding optimum camera positions to see as much as possible at once. We use the simulated annealing approach to find the optimum camera positions. This guarantees that we find a global solution to the optimization problem. Here we can see how the method finds the optimum camera position for the optimum mirror and for InverseVis, as well as the optimum parameters for each method. Finally, we tested the methods on various surfaces and noted the overall visibility achieved. InverseVis performed best on all surfaces tested. Thank you for watching the video.